Okay, hello everybody. Today we're talking about how to differentiate using the chain rule. Now this is how we differentiate composite functions, so a function within a function. We're also going to talk about how to differentiate rational powers, so that's when we have powers which are fractions, and this will also involve use of the chain rule as well. Okay, so let's get started. So the chain rule, like I mentioned, it's used to find the derivative of a composite function, a function within a function. You'll remember earlier this year we looked at developing composite functions, for example f of g of x, so a function within a function. So for example, if f of x equals x squared and g of x equals x plus 2, and we're finding f of g of x, we were substituting our g of x function, x plus 2 here, where the x would go for our outside function, our f of x function. We need a square here, squared here, because that's finishing off our function within a function. So what we're going to be doing is looking at differentiating functions like this. Now obviously in this particular case, that we can see here, one way to differentiate this would be to expand our rule. So if we were differentiating this conventionally, and when you were in methods units 1 and 2, what you would do is expand this function to give us x squared when we're expanding a perfect square plus 4x plus 4. And if I was now differentiating my function, my f of g of x function, so if we're differentiating that, we would then multiply by the power, subtract 1 from the power, multiply by the power, subtract 1 from the power, and our constant terms, of course, that's the same as x to the power of 0. So if I multiply by the power of 0, 4 times 0 is 0, so our constant term becomes 0. And this would be our derivative. Our chain rule, it's written in the most common way down below just here. And essentially what we're saying with our chain rule is that we differentiate dy du with respect to one function and then du dx. So in this case, we're differentiating the outside function and the inside function. So if we're thinking about what's going on here, we can differentiate our inside function. So if I differentiate our inside function, our g dash x, we would just get 1. By differentiating our outside function, f dash x, we get 2x. And what we're doing then is that we multiply our g dash x times our f of x, but our outside function needs to have within it, instead of x like here, we substituted g of x where the x was. So we do the same thing here. We substitute in our g of x part, our x plus 2, to give us a derivative of 2x plus 4, which is the same thing. Now the way this is written can be somewhat confusing, okay? So we tend to actually generally set this up in a different way, and that's what I'm going to go through in just a moment. So more often the chain rule is written this way. We differentiate to find dy dx, we determine a new variable u, we differentiate y, so dy dx. When we're talking about that, what we mean there is that we differentiate the y function with respect to u, and we multiply that by differentiating the u function with respect to x. Okay? So we differentiate y with respect to u and then differentiate u with respect to x. So let's start looking at some examples. If we are differentiating our first function here, now remember our function is to find dy dx. We differentiate y with respect to u and then u with respect to x, and we multiply those two things. What we need to do first is to determine for our composite functions what the inside function is. So if this is a composite function, the inside function would be u equals 2x plus 3. And we determine an inside function, and typically we use u to represent the inside function. The outside function, if I've substituted this u inside here, it is sitting within the outside function of u to the power of 7. So I'm choosing to let 2x plus 3 equal u. This is the inside function. Now, I need to differentiate both of these. I need to find du dx, and I need to differentiate to find dy du. So here, to find du dx, I'm differentiating u with respect to x. So when I differentiate with respect to x, the derivative of 2x is 2, and the derivative of 3 is 0. If I differentiate dy du, the derivative, and we're differentiating y with respect to u, so it's the u I'm differentiating. I multiply by 7 u, and I subtract 1 from the power. So to put this together, okay, the chain rule says that dy dx is equal to dy du multiplied by du dx. So if I'm working that out, dy du, that's going to give me 7u to the power of 6 multiplied by du dx is 2. If I simplify this, I get 14u to the power of 6. But this is not a good derivative. We want to differentiate y with respect to x. So what I do just at the end, because I'm wanting to substitute y with respect to x, is that I need to substitute my value of u back into my equation again. So I'm substituting that back in for our value of u down here. And that would give us 14, and instead of u I write 2x plus 3. And this function, our u, is to the power of 6. Now, it is not a good idea to expand this. If we were expanding this, we would just be making life a little bit difficult for us. There's a greater risk of making a mistake. There's absolutely no need to expand. I'm just going to stop before I go on to the next example, because I think it's important that I just prove to you why this actually works with a more simple function. So let's think about the one we were doing on the previous page, or something similar. If I had the function y equals 2x plus 1 squared, if I was expanding this, I would get 4x squared plus 4x plus 1. And if I differentiate this, dy dx, I multiply by the power. 4 times 2 is 8. Subtract 1 from the power is x. Multiply by the power. 4 times 1 is 4. Subtract 1 to the power. That would give me x to the power of 0. But we know that x to the power of 0 is equal to 1. So therefore I don't need this term there at all. So this is how we would have differentiated it using methods 1 and 2. If we instead decide that we're going to let our inside function here equal u, that means u will equal 2x plus 1, our inside function. Our outside function y, we're letting 2x plus 1 equal u, so I'll instead have u to the power of 2. If I differentiate du dx, so I'm differentiating u with respect to x, the derivative of 2x is 2, and if I find dy dx, the derivative of u squared multiplied by the power and subtract 1 from the power give me a power of 1. Using the chain rule says that to find dy dx, we have dy du multiplied by du dx. So I can differentiate this. Dy du, I can substitute into here. Dy du is 2u times du dx is 2. 2 times 2 is 4. Instead of u, I'm going to get our function from before, our value of u that we established, which was 4 4 multiplied by 2x plus 1. What you should be able to notice here is that these two derivatives are the same. If I expand this derivative here, I would get 4 times 2x gives me 8x, which is what we had up here. And if I was expanding here, 4 times 1, that would give me 4, which is what I had over here. You need to make the decision, when is it more useful to expand, which I think it probably was in this case, or when is it more useful to use the chain rule. Now in this case perhaps using the chain rule was more work, but back in our example A here, if I was expanding this, there is a high chance of going wrong, so using the chain rule was of advantage here. Okay, with our next example that we're looking at, in this case we've got a rational function. In this case we have to use the chain rule, there's no other thing we can do. So we can rewrite y. Let's use brackets here because this is the same as saying 2x minus 5 square root is the same as the power of a half. When we're using the chain rule, we find the inside function. The inside function is this part here, the 2x minus 5. So we will let u equal our inside function 2x minus 5. That means that y equals, if u equals 2x minus 5, we will have u to the power of a half. I differentiate both of these. The derivative of 2x is 2. The derivative of negative 5 is 0. dy du, I'm differentiating y with respect to u. I multiply by the power and I subtract 1 from the power. Then we're up to using the chain rule. So dy dx equals, the chain rule is dy du and multiplied by du dx. The chain rule is found on your formula sheet, by the way. Dy du, that will give us a half u to the power of negative a half. I might actually write this as u to the power of half in the denominator. Remember to make powers positive. We had a negative power up here. To make it positive, I can move that pronumeral to the denominator. Multiplied by du dx, which is 2. So if we're looking at this, we can cancel. The 2's divide by 2 times by 2 cancels, and I get 1 over square root of u, which is, or u to the power of half, which is the same as the square root of u. Finally, we wanted a derivative with respect to x, okay? Our derivative we were looking for was a derivative with respect to x. Our answer we've got at this stage is a derivative with respect to u. So I need to substitute in our value of u. So I will end up with the square root of, instead of u, I get 2x minus 5. We're going to differentiate again. Now I want to show you, we were setting up before our functions separately. Remember again the chain rule, dy dx equals dy du multiplied by du dx. So what we were doing was we were defining the u. And you are absolutely welcome to continue defining the u in that way. There is another option, however, and our other option is to think of it a slightly different way. So our shortcut that we can use, and this is optional, you do not have to use the shortcut, this is optional, is to think that what we do is we multiply the outer derivative, so we differentiate the outer function, and we multiply that by the derivative of the inner function. So we differentiate our inner function. Let's try using the shortcut for this first example here. So to differentiate dy dx, our outer function is this here. Something to the power of 16. So to differentiate to the power of 16, what we do is we multiply by our power. We keep whatever the inside thing is there, whatever it is, it stays the same. We're just differentiating the outside part. So to differentiate the outside, we multiply by 16 and we subtract 1 from the power. Whatever was inside, that stays the same because we're just differentiating the outside part. And we multiply this by the derivative of the inside function. So our inside function is this part here, the 4x squared minus 3x plus 5. So I multiply this by the derivative of the inside function. The derivative of 4x squared, I multiply by the 2, that gives me 8x, subtract 1 from the power, so it's the power of 1. Minus the derivative of 3x is 3, and the derivative of 5 is 0. This is more or less my final answer. Once again, there is no need to expand. That just risks making mistakes. Generally, we tend to write the brackets with smaller powers first, but it really does not matter whatsoever. And so that's a shortcut way to get to our answer. I'm going to just reiterate how to solve this with the chain rule. Feel free to fast forward if you quite like that shortcut method, but if you prefer the chain rule, I'll go through it quickly. So the other option using the chain rule is that we determine our inside function u. The inside function is 4x squared minus 3x plus 5, and the outside function then would be y equals u to the power of 16. We differentiate dy with respect to du. Multiply by the power and subtract 1 from the power. You can see this is the same as what we were doing in this first step here. Okay? Except that in the shortcut way, instead of defining u, we left the inside function as is, unchanged. We differentiate du with respect to x. That gives me 8x minus 3. And we'll notice this is the same as what we get when we differentiate the inside function here. Then the chain rule says that to find dy dx, we have dy du multiplied by du dx. dy du is 16u to the power of 15 times du dx. Make sure we've got it in brackets. We're multiplying by this entire function there. Equals, instead of u, we substitute back in our value for u that we had defined up here, and so it would be 4x squared minus 3x plus 5 to the power of 15 multiplied by 8x minus 3. So it is entirely up to you. We have got two methods there. It is entirely up to you whether you prefer to use the shortcut method as shown here or the extended using the full chain rule down below. Whichever you are more likely to get correct and whichever is most likely to be efficient is the way you should choose. Let's have a look at our second one. Now this second one is actually tricky because we have a whole lot of functions within functions. We have our largest outside function, which is this one here, the square root. And we might actually write that to the power of a half. We then have our function within that, which is our function here of 4x minus, and we're going to have to use the chain rule again for this part, because again we have an outside function just here. So we've got our 4x minus, and we've got another outside function here. Within that, we have our inside function again of 2x plus 3. Okay, so let's start thinking through carefully what we do. I'm going to use the shortcut method first. To differentiate the outside function, I multiply by the power, which is half. I leave whatever is inside exactly as it is because I'm not touching that right now. I'm just dealing with the outside part. And I subtract 1 from the power, which is negative a half. Okay? The inside stays as it is because I'm just differentiating the outside function. Then I differentiate the inside function. So the derivative of 4x, and let's put it in brackets because I'm multiplying the entire inside derivative by the entire outer derivative. So the derivative of 4x is 4 minus the derivative of, now we've got another chain rule, we have to use the chain rule again. So I multiply by the power is 6, this is the outer function, and within that I then multiply by the inner function, the inner function stays as is, and I subtract 1 from the power, which is 5. I can't close my, I'm doing the inside of the purple function, but I also need to differentiate the inside, this little bit here, the derivative of 2x times 3, that's multiplied by 2. The derivative of 2x is 2. So this is what I'm looking at here. This is the function that I need to deal with. Now let's write this as one fraction. Let's tidy it up a little bit. So we've got a whole lot of things that can belong in the denominator. We've got this purple 2 here. We've got our whole function here, which has a power of a negative half. Remember, negative powers can go to the denominator, and instead of writing a power of a half, we can write it as a square root. So we've got 4x minus, oh, and I forgot my 6 there of my copying my inner function exactly. Sorry about that, everyone. Of 2x plus 3 to the power of 6. And then in the numerator, I will have this part here. So I will have the function of 4 minus 6 times 2 is 12 of 2x plus 6 to the power of 5. We can cancel out because in the numerator we can take 2 as a common factor. Well, actually we can take 4 as a common factor, but I'll just take 2 to make my point for cancelling here. Over the square root of 2, 4x minus 2x plus 3 to the power of 6. And we can cancel out our 2's there to lead to our final answer. So this was using the shortcut method. Now if you had decided that you wanted to solve this instead using the chain rule, we can do that as well. And if you're wanting to solve this function using the chain rule, bear with me and we'll go on to the next slide. If you're happy using the shortcut, then feel free to end the video at this point. Okay, so this is just showing again how we would differentiate this function like we did on the previous slide, but again we're looking at doing it this time using the chain rule. So if we start by looking at our outside function, we can define this part in here as being our function u. So we could get y equals the square root of u, that's the outside part. The inside part would then be u equals 4 minus 2x plus 3 to the power of 6. The problem is that we need to go a bit further because we still have this function here to deal with. So we can set this up again and choose another variable. We can say that u is actually the same as 4 minus, instead of 2x minus 3, I'm going to call this v. So I'm setting another variable, v, to the power of 6. And that means that v is equal to that part inside 2x plus 3. Our u here we can write as u to the power of half. We need to write powers rather than square root signs to be able to differentiate effectively. Okay, so we're ready to differentiate. I differentiate dy in terms of du. Multiply by the power, subtract 1 from the power. I multiply u with respect to v. The derivative of 4 is 0. The derivative of negative... Oh, and I'm very sorry. Hold on a minute. Sorry. Oh, what have I done? Almost made a mistake there. This should have been 4x here. 4x, 4x. Terribly sorry about that, everyone. Okay, So the derivative of 4x is 4 minus the derivative of v to the power of 6. I multiply by 6 and I subtract 1 from the power. Finally, I need to differentiate v with respect to x, and I get 2. The chain rule in this case, we need to use all three parts. To get dy dx, we're going to have dy du multiplied by du dx by dv dx. Now what you might notice here, and this is entirely not a good way to think about it, but it's almost as if we can cancel out du and du, and dv and dv cancel out, so it's still dy over dx. Now we really can't cancel things out that way, so please don't try, they're not like normal fractions, but it does give you an indication of why this will work. So let's substitute in our values. Instead of dy du, I will get a half. Well, let's actually write this as a fraction, 1 over 2 square root of u. Instead of du dv, I get 4 minus 6v squared. Make sure we're using brackets to keep that whole derivative together. And then we multiply it by 2, which was dv dx. Divide by 2, multiply by 2 cancels out. So we get 4 minus 6v to the power of 5 over square root of u. Finally, we can substitute in, we were wanting the derivative dy dx, so I need to substitute in the values of v and u, those functions. So I would get 4 minus 6, instead of v, we have what we had to find up here, 2x plus 3 to the power of 5, and that is all over the square root of, instead of u, we have the function defined earlier here. We have 4x minus 2 lots of 2x plus 3 to the power of 6, and this is the same as the function we got by using the shortcut. Whichever you find easier is what you should be doing. One final example. We're wanting to find this derivative here. When it says find the derivative, we need to have some way of writing this. We could either let y equal our function. Another way is saying that I'm going to differentiate this function, this function here, and I might even rewrite it with powers instead. So I'm going to differentiate this function with respect to x. When we've got a 3 here, that means that our power is 1 over 3. Remember, for a normal square root, that's a power of half, and we assume there's a 2 written there, even when we can't see it. Let's differentiate using the shortcut. So the outside function, I multiply by the power. I'm keeping the inside function the same because this is the outer derivative I'm doing right now. So I multiply by the power to give me 1/3. I subtract 1 from the power. So I'm doing 1 minus 1/3, which gives me negative 2/3. And then I multiply by the inside derivative. The inside derivative, I differentiate this part here. Derivative of x squared is 2x, and the derivative of 5x is 5. So we can write that as 2x minus 5 over 3 lots of x squared minus 5x to the power of 2/3. We can leave it like this. This is entirely acceptable. Or if you choose, because we have this 3 in the denominator here, that can be written as a cube root. So it is also fine to continue on and write your answer as 2x minus 5 over 3 lots of the cube root. You just need to be very careful about the difference between the 3 as a constant that's been multiplied and the 3 as a cube root of x squared minus 5x, and this is all still to the power of 2. Either answer is acceptable. You can leave it like this, that's fine, or in this option as well. Okay, so that's the chain rule. You can use it for differentiating a whole range of different functions when we have our composite functions, one function within another.